and interpretation in voxel-based soft robots, a part assembly approach with Bayesian optimization.
Hello, this is Mizuki from Japan, and I'd like to present a work by one of my PhD students, effective design and interpretation of voxel-based soft robotics. So it's about an algorithm proposing to come up with a more diverse and competitive soft robotics. So as you all know, the soft robotics are composed of soft materials, and they offer greater design freedom and variations compared to hard robotics. And they're modular, and they provide expressiveness and promising for diversity. And here is, for example, a simulation called Evolution Gym that offers to simulate one of those soft robotics. And in this simulation, they offer 4 types of voxels: static, rigid, and soft. They kind of correspond to bones and fat, and 2 actuators, horizontals and vertical. So you can think of them as like more muscles. And by arranging these types of 4 voxels, you can come up with one design space. And in this evolution gym simulation, you can kind of train the agent to move forward given this task. And there's many interesting approaches that allows us to evolve different types of designs. And the representatives ones are genetic algorithms and compositional pattern producing network. And they can come up with, if you train these algorithms, given, these algorithms to evolve, you can actually come up with different types of robotics design given a task. So you can actually see a really nice agent coming up. But here's still some challenges for designing voxel-based robot designs. And one, of course, being the large design space. So it requires high computational cost, and it also has scalability issues. And because it's a soft robotics, it has design flexibility, and it kind of makes it difficult to balance flexibility with functional requirements. So sometimes it fails to find the functions that it requires for the robot to complete a task. And often these algorithms, given the final design, it's difficult to interpret why the design choices are made for particular functional implications. And so for example, if we use GA to design robots, these are the kind of designs that you can come up with. And the strengths for using GA, that it optimizes designs over generations, it can handle complex design spaces, but weaknesses are they could get stuck in local optima, limiting the diversity of globally optimal designs. And it sometimes limits the interpretability of the resulting designs, which sometimes make it hard for the human people maybe to optimize further. And the same for CPPN, it generates complex patterns from simple functions. So you can actually see that are more moduled, and they become maybe flexible and adaptable designs. But again, they suffer in complexity in controlling fine-tuning, and also again, limits the interpretability of the resulting designs. So given that, we are proposing a new algorithm that's called part assembly with Bayesian optimization. And this algorithm has 2 key ideas. One is to simplify design space by proposing the parts of the robots instead of like a grid, cell-based exploration. This constrained design space gives a more efficient exploration. And we also define a feature space, continuous feature space, which allows us to give probably, hopefully, more diversity as well as the interpretability of the resulting design. And these 2 features, we hope to improve the design exploration and gives higher interpretability of the resulting designs of the robots. So for the first idea is that we come up with parts of the robots. So kind of we give the parts instead of one single cell. And then we assemble these parts randomly to design. And also we define these global and local features and project them into this robot into this future space, which hopefully will allow us to explore the design space more effectively. And given this continuous feature space, we use Bayesian optimization to find optimal design, which will be using acquisition function. We will be using a random forest for the acquisition function. And sorry, so we'll be using surrogate Bayesian random forest for the surrogate function, and we'll be using expected information for the acquisition function. So we kind of iterate this process to find an optimal robots design. So we conducted, using the proposed method, we conducted experiments using this benchmark called Evolution Gym. This was proposed by MIT group in 2021, which allows us to evolve the design and its controller. So they have about 32 benchmarks, tasks already set up in the simulation. So we chose 8 benchmarks out of 32, which are representative for different types of tasks, which are listed here. And we compared 3 algorithms, so GA, CPP, and NEAT, and this Bayesian-based optimization with parts assembly. So we repeated, repeated this experiment till it finds 1,000 designs, and the whole experiments were repeated 3 times for reliability. And here is some of the results, and I'm showing one benchmark. That's the task is to come up with a robot design that can throw a rectangular shape as far as possible. And you can see that our method is actually compatible or comparable with the existing methods. But if we look at, and these are some of the samples that had high fitness, the design that came up with. So you can actually see that ours may look like they have more diversity. And if you actually try to quantify the diversity of the found robots, actually we actually see that diversity is higher in our proposed method, where the diversity is actually measured with edit distance given a group of robots. So because we use random forest by analyzing the future importance of the random forest, we can actually see which part contributed to the higher fitness. And in the thrower task, we can see that the virtual actuator, which is in blue color, have had the higher importance in the task of throwing. But we can also see that other features actually did not contribute to much of the performance. This kind of gives us space for improvement of the hand-designed features we came up with. And another quantitative evaluation of our method that can be done by using partial dependence plot, which allows us to see which part of the design was effective in achieving a higher fitness. And for example, in the thrower, we can see that upper right corner has a higher fitness, which means that having this virtual actuator in blue, having that part on the upper right corner is very significant in achieving a higher reward in this task. And you can actually see all the robot designs that this algorithm found we indeed have this virtual actuator placed on upper right corner. So you can see that having this kind of shape on top of the right corner allows the agent to be able to throw that object farther, right? And this one has the highest fitness. The next highest fitness robot has kind of the black shape, but that probably doesn't count much to the higher fitness, but this soft vertical actuator really indeed give a good performance. So our algorithm kind of allows us to analyze or give a more interpretability of the design found. So here are some key takeaways. So we proposed part-based design optimization using Bayesian optimization. And this design principle enhances diversity and interpretability compared to the existing methods while maintaining the performance quite competitive to the existing ones. And that indeed the part positioning is very crucial for task performance in software robots. So we could actually confirm that. And so that, and hopefully this part-based approach combines human intuition with computational motivations and making the software robotics more accessible by making the design interpretable. And hopefully that will contribute more when these simulated software robotics would be actually implemented in reality. Okay, with that, thank you for your attention.